All right, folks, let's go ahead and get started here. So my name is Ron Ortloff. I am a program manager on the Azure SQL Data Warehouse team. Today we're going to talk to you about Gen2 and turbocharged analytics on Gen2. From agenda perspective today, we're going to talk firstly about the modern data warehousing architecture, how we can maximize ROI on basically a reference architecture that we're pitching. Then we're going to talk about how we've moved from Gen 1 and move forward on an architecture perspective into Gen 2. We'll go a little bit under the hood on the adaptive caching capability that we've offered in Gen 2. Talk a little bit about how sizing is a bit nuanced with the Gen 2 platform. And then some software perspective goodies that we put into the Gen 2 platform with resource class improvements, and then also instant data movement and some of the performance benchmarking that we've done on Gen 2. So I'm fine, you guys, if you want to ask questions. There's mics up front. Feel free, come on up and ask a question. I don't anticipate speaking for 75 minutes straight, so we will have plenty of time at the end for questions as well. And I've got some swag that I need to hand out to you guys as well, so we'll make sure we get out of here on time. So the whole idea with the modern data warehousing architecture is folks are going through, for one reason or another, moving out of a data center. They've got hey, we've got too much OpEx, we've got too many servers and data centers, let's shut them down, let's migrate things to the cloud. My license for XYZ product is up this summer. Hey, let's, instead of re-upping our license, let's move up into the cloud. For one reason or another, folks are wanting to migrate things to the cloud, but while they're doing that, they're looking at more of a way to modernize and get more return on that investment as they move into the cloud. And basically, the modern data warehousing architecture is a reference architecture, helps you guide you for the right service for the right job. And that could be transfer and store data, process and cleanse data, and then also serving and analyzing data. So we'll walk through a few slides here on different components within that reference architecture. And we'll start first with unstructured data. How can we get that into basically a general use platform, general use architecture? So you can use the Azure Data Factory service, pull that data unstructured in, do some processing on it if you need to, drop it into blob storage, and have it persisted there. On the bottom part here, this is where your line of business, your structured data, sales data, CRM data, that sort of thing. Maybe you've already migrated some of your transactional stores to SQL DB, and those are up in the cloud already. Again, you can leverage Azure Data Factory, set up your pipelines, extract from the structured data sets, and now have them up in the cloud for you to access. So now we can start stitching this data together. We can use Databricks now, pull that data, that unstructured data off of Azure Blob Storage, cleanse it. If you're going after like social, Twitter feeds, blogs, unstructured data, you want to trim out all those buzzwords, and also maybe start marrying it with some of that CRM data, that sales data that you have on-prem, and getting a normalized taxonomy. So here you can pull data using Azure Data Factory, dumping it into blob storage, pulling all that data into Databricks, and now really having a cleansed, clean data set that you can then serve up into Azure SQL Data Warehouse. There I'm pulling in my unstructured data that's been cleansed and processed in Databricks, and then maybe I just have direct pipelines that are coming from transactional stores and going directly into the DW serving layer. So now I'm in SQL DW. I've got a known schema. I've got interactive querying. I can hook up Power BI for some simple dashboards. I can point my models here, learn, train my models, and then I can let my data scientists kind of go crazy on the data as well. All right, so that's modern data warehousing. Let's jump into Gen 1, Gen 2 architecture perspective. So when we first GA'd SQL Data Warehouse on Azure, we kind of broke the mold with this whole concept of separation of compute and storage. So we have on the left-hand side here, control, compute, and remote storage. And this was great from an elasticity perspective. You could scale down your compute, you could scale up your compute, you could even pause your compute. So just pay for storage and not have to pay for compute. Unpause, surface compute, continue your processing. From a physical architecture perspective, again, on the left-hand side, this concept of control, compute, remote storage, that still holds true. Now let's take a look at it from a physical kind of perspective. So each one of these nodes, whether it's control or compute, has cores in memory, obviously, and then some solid-state disk on it for TempDB. Faster access, more transient data, that sort of thing. And then on the bottom here, we see remote storage. So this is where your database data and log files sit. With this version of the service, we've got 60 distribution databases. All of those databases have 4 data files attached to them at 1 terabyte each. So 60 times 4 times 1 terabyte, we have 240 terabytes of addressable storage. We always say with roughly a 5x compression ratio on your clustered column store indexes, you can get about a petabyte's worth of data stored into a SQL Data Warehouse on Gen1. And you'll note here in the bottom with the data and log files, one thing that I want to highlight. So we have both row store and column store data that's stored in these data and log files. So we would get into POCs with Gen1. Folks are like, hey, here's the feedback. Love the elasticity, love the ability to pause and resume. I can size my compute. Other providers or other data warehousing providers in the cloud require you to actually scale your compute to also scale your storage. So we like that Azure SQL Data Warehouse has decoupled these, but the performance, not so hot, right? Do something about the performance. So this is where we come forward now with the Gen2 architecture. We kind of challenged ourselves, hey, let's keep those good aspects, those things that folks valued in the service, the elasticity, the pause, resume, but let's go after this performance problem that we have. And a lot of that came around the issue with our separation of compute and storage. So what was so good for us was also hindering our performance. When you think about I/O latency, remote I/O is about as bad as it can possibly get. So what we did with the Gen2 architecture is we actually inserted between the compute layer and the remote storage layer a caching layer, what we call the adaptive cache. So if we go back to this architecture diagram, now we see some things have changed. Again, same control, compute, remote storage layer, but now we've got a larger SSD cache, this NVMe SSD cache. So much larger, much more performant, higher capacity for us to now chop that up and have a similar TempDB footprint as we do on Gen1, but also set aside some space for caching data closer to compute and eliminating that remote I/O penalty that you always had on Gen1. The other thing you'll notice here is these little hash marks on the bottom. So this is a representation of your column store segments. So the row store segments are still residing inside of the distribution databases, inside of that 240 terabyte limit that we have. But now we've taken the column store segments and pushed them out into their own remote files. What this gives us now is basically limitless storage for clustered column store segments. Now we can do that for those that are familiar and well-versed in clustered column store technology. As the segments come in and they're compressed, they're immutable, they're read-only. All right, so we can dump those out the files, and then all of the semantics and inner workings of CCI with Delta stores and being able to convert and move data and still present a consistent target just takes care of itself. So what this happens now then, as segments are read, you do your large table scan aggregates, the data is then pulled off of the remote storage and pushed into the local cache. From there, then I can continue to operate on that data without having to pay that remote I/O penalty. So if you take this forward, you get this nice little beautiful triangle diagram here, and this represents, in essence, the automated tiering of the storage layer. So if you think about your hot data living and residing in your main memory, you're going to have a very, very quick access time, but a smaller capacity. In the absence of Gen 2 now, you went straight from main memory all the way out to the remote storage, which is a significantly higher access time. So to combat that, then we introduce this adaptive cache in between those that gives you pretty decent access time relative to the remote storage. Key takeaway, though, with this is all of this moving between remote I/O and adaptive caching, this is all seamless to the end user. All right? We take care of migrating data into cache. We take care of pushing data out of cache. So with that said, let's take a look at how this kind of works underneath the covers. So Kevin up front here, these are his slides. You can throw apples at him if you don't like them, right up here. No, I think they're pretty awesome. That's why I stole them. So, well, let's walk through kind of how data flows in and out of cache. You kind of see some fun animation here and how things kind of all piece together. So let's start off. I've got my classic aggregate query here in the upper right-hand corner. Select total cost from your fact sales, which is clustered column store indexed. So first off, we're going to check the column store object pool, see if the values are there. If not, we'll go to the adaptive cache. If not, we'll drop down to remote storage, bring that value up into the adaptive cache, the column store object pool, and then return to the query. Fantastic. Now, any sort of a repetitive read against that object doesn't go through that same cycle. Just goes straight from the column store object pool and is pulled into the query. This is standard caching that happens within SQL Server. If you drop clean buffers, so remove your data from the column store object pool, you'll drop data out of the column store object pool, but the adaptive cache remains intact. We'll update the costing info, but the data itself still resides in the cache. Now, if you pause or scale, because you're actually removing and changing the compute layer on top of that, that will actually clear out the cache. So in this scenario here, we've got a full cache, and we're pulling data in through a query here. So again, our same classic query, check the column store object pool, check the adaptive cache, which is now full. If there's a miss there, then we do the remote read. Your kind of classic sort of LRU algorithm kicks in. We punt out the value that's been least referenced, make room for the remote read, and then the normal query cycle continues. Okay, so that's kind of adaptive caching underneath the covers. Let's take a look at how loading on Gen 2 works. So there are some kind of nuances here that you'll want to watch out for on the Gen 2 platform when it comes to loading data. Kevin's going to do a theater session. I highly recommend you guys attend that one if you have further questions on data loading. So here, if I'm going to run a standard kind of create table as statement, a CTAS statement, this is like a poly-based load coming from an external set of files via an external table. When I issue that create table statement with a clustered column store index on the build, it's going to write the data from external files directly into column store segments if I have enough memory in the query and I'm loading enough data itself to be all compressed. Now when I do my standard aggregate query, then I have to pull all that data off of remote storage and pull it into the column store object pool. taking a slight twist on this now, same kind of syntax with the CTAS statement, but now we're going to load into a heap. So just a refresher, heaps are row stores, they're not column stores. So this is pulling data off of external files and then transferring it directly into the distribution database data files as row store format. Your same query then pulls the data, does that remote I/O, and pulls the data directly into the buffer pool. Again, because this is row store, we're not going to push that into the Gen2 adaptive cache. All right, so row store data is not cached. Similarly, kind of carrying this example forward, if you load into a temp, so a pound temp table, something that goes into tempdb, there again, you're going to pull data in through as a heap and persist that in row store format into tempdb. A select aggregate on that query pulls the data out of tempdb into the buffer pool. So my access point now for that row store information, instead of coming off of remote I/O, is coming off of NVMe SSD, very local, just like it was actually put into the Gen2 cache. So if you're loading data and you want to do ELT, it's best to get that data into tempdb or even load it as a heap so you're not transiently kind of trashing your cache, so to speak. Let's take a quick look here at some execution time. If I can get out of here. Okay, this is not an exhaustive example here. This is just something to kind of whet your appetite a little bit. And so let's drop clean the buffers here so we're playing on the level playing field. Drop the table. So this first one here, so this is clustered column store index loading. We're doing a hash distribution on the supplier key. The source for this is also hashed on the same value. So this is going to be a distributed CTAS operation. There's going to be no data movement involved. And this is just pure raw performance, how fast you can load data basically from the Gen2 cache, because I've ran this query a few times. Even though I drop clean buffers, it's coming out of the Gen2 cache. How fast can I write this into a target? So you can't see the time. It's too small. This thing ran in 8 seconds. Let's repeat the same cycle here. So this example now is loading data into a heap, same source that we're using to pull the data from, same distribution target, but instead of loading into clustered column store, we're loading into a heap. And that ran in 5 seconds. So 8 seconds for the CCI load, 5 seconds for the heap load. Now the last example here. So 8, 5, and now this one loaded in 3 seconds. Okay? So now I've got data in SSD cache in row store format that I can access very fast because it's closer to the data. So kind of dry residue on this. Why does this matter to you? Why should I care? Thanks for sharing that, Ron. So a lot of times when you're doing ETL processing, especially in old school kind of delta processing that you would do on your data warehouse, you're going to extract some kind of data, process it, scrub it, bring it in locally, kind of stage the data, and then you're going to fold it into kind of your final fact tables, or you're going to fix up a dimension, kind of standard garden variety data warehouse processing. Given now that you kind of have these details around how to load data into Gen2 and also how to sort of play nice with the cache, these are some tips or some tricks that you can leverage as part of your ETL processing. Put things into heaps, put them into tempdb if you want. That way you're not going to be polluting that Gen2 cache with data that you're really going to load up once and then probably drop anyways, right? You want your final fact tables to have the cooked, the processed data. You want good CCI compression there. You want to ensure that those things actually stay in the Gen2 cache. So these, if you follow this kind of pattern, and again, this is what we're seeing some customers kind of shoot themselves in the foot with by doing CCI loads into literally like, temp underscore customer dimension. They load up data, fold it into the dimension, and then you see 2 lines later they drop the table, right? So now that data's been pulled into the Gen2 cache and then dropped, and it'll never be used again. So this is just some tips around that particular scenario. All right. So when it comes to sizing Gen2 cache and just sizing Gen2 in general, a couple things that you're going to want to take into consideration now that you have some details around how the Gen2 caching is being leveraged. So with Gen2, we talk about having that warm data set all kind of residing in the Gen2 cache. We kind of refer to that as your working set of data. A good rule of thumb is to kind of do your SP space used on your data warehouse and start off with, hey, roughly 20% of that should be my working set. That's typically what we see with customers. Now, that's just typically, all right? Certainly, there are data warehouses out there that are very, very hot, a large portion of them that are in their working set. But as a good kind of general rule of thumb, you can start with 20% of your SP space used and then size that into a DWU setting. That should be able to hold that data for you. Also note too that TempDB is the same on Gen 1 and Gen 2. So per DWU, your TempDB space is going to be equivalent on both Gen 1 and Gen 2. And the reason that I do call that out, we are seeing a lot of customers migrate from Gen 1 to Gen 2, absolutely love the performance, and then start playing around with actually scaling down their DW instances to try to save a little bit of money. Totally makes sense, right? But they've kind of sized their workload, their ETL patterns, their query patterns around having this expected amount of memory, this expected amount of concurrency, this expected amount of TempDB, and now when they're scaling down to save a few bucks, things start to run a little bit wonky on Gen 2. So working set, get that, understand kind of roughly what data volumes you're working on, and then from that point forward, take a look at some of the metrics that we have now for caching. So we introduced 2 new metrics in the portal for Gen 2 and for portal monitoring for cache metrics on Gen 2. The first one was the cache hit percentage. So simply just cache hits divided by cache miss. And this again is just for the CCI segments that we're trying to cache for Gen 2. And the other metric is cache used percentage. So what we've got here on this slide is kind of just a simple matrix of decisions that you can take a look at based on the values you get from those metrics. So if you have a high cache fill ratio, so my cache is percentage-wise pretty full, and I've got a high cache hit ratio, I'm actually in kind of that optimal usage scenario. If I have a high fill ratio and a low cache hit ratio, so my cache is full, but my hit ratio is still pretty small, I could consider scaling up to give myself more cache. Low cache fill ratio and a high hit ratio, so I haven't filled up my cache, but I have a very high hit ratio. Here I could consider, in the grander scheme of things, assuming I'm not bound on CPU, I/O, TempDB, that sort of thing, I could consider scaling my instance down. And then lastly, I have a low fill ratio and I have a low cache hit ratio. So I'm not having a lot of hits to the cache, and also I don't have a lot in the cache. That could be a scenario where I'm in cache hydration. So let's pop over to the portal. How does that show up for folks? So this is a demo instance that I've had up and running. So boy, that's pretty hard to see. basically the two lines here, blue line up on top here is the cache hit ratio, and the bottom purple line is the cache fill ratio. This isn't all too interesting. I did capture a screenshot as I was warming things up before. So you can see this purple line here, the cache fill ratio. As I just unpaused the instance and I was running some queries, you can see this incrementally popping up as the cache is being hydrated. The cache hit ratio was still pretty high because it was doing a good job of getting things cached prior to them being read. So there's going to be different kind of signatures, different sort of patterns that you'll see with these caching metrics. And certainly with the information that you have on how caching works and the metrics and the stuff that we just discussed, you can help kind of right size your cache for your workload. Okay, so let's switch gears here a little bit. I've kind of gone plenty deep enough on the caching stuff. And let's talk a little bit about resource classes on Gen2. How many folks, just quick show of hands, see if you guys are still alive. How many folks are familiar with resource classes on SQL DW that are using them? Okay, good, half the audience. All right, so on Gen 1, we had some kind of legacy, I don't want to call it baggage, but we had some kind of legacy stuff that we carried forward from our old days on-prem with APS into the cloud and into SQL DW. And we took Gen 2 as an opportunity to kind of smooth over some of those rough edges around resource classes in Gen 2. So first things first, let's just kind of level set because half the folks in the room aren't overly familiar with resource classes. Let's just get a couple concepts, some base foundation set here. So with SQL DW, we support up to 1,024 open sessions, and we support at our DW 6000 and above, we support 128 active concurrent queries. So lots of folks see those numbers and they ask questions, hey, why do you guys cap concurrency? Why are these limits existing? And it all has to do with the fact that we have to pre-allocate memory prior to queries being scheduled. So think of a scenario where you can run into a distributed deadlock where you have two of these separate compute nodes that are fighting for the same memory. Now, if you end up in those scenarios where you've read data off of disk, put it into your memory, you need more, and another query is basically in the inverse situation, you guys will be waiting on each other forever. This is a little different than CPU and I/O, where those can be very short compute quantums. They can run their sort, run their aggregate, and then be done with it. They can do their I/O off of remote disk, pull it into memory, and be done with it. But we have to allocate memory for joins, sorts, aggregates, those sorts of activities. And we have to hold on to it for the duration of the query. So this is why we have to limit the amount of concurrent queries that are running to ensure that we have the ability to allocate memory to queries prior to them being scheduled. The other thing we have to consider too is underneath the covers, so SQL DW has 60 distribution databases. And when you issue that aggregate query or that select query from a table, we actually have to fire that query to each of those distributions. So if you do the math, 128 actual executing data warehousing queries times your 60 distributions, you're over 7,000 active running connections, which is quite a bit. It's quite a bit of information for the control node to hold on to and make sure that those connections are active and responsive. So we can certainly go higher, but there are issues around connectivity within just the SQL DB nodes and coming into the control node. So given that we just covered how memory is allocated and how it dictates query execution, let's talk a little bit about how memory is actually allocated. So you have a total pool, a total amount of available memory to a system, and that's dictated by the DWU setting that you have. So on DW1000C for Gen2, you have a total of 600 gigs of available memory that you can address. That scales all the way up to DW3000C, where you have 1.8 terabytes of memory that you can address. So big, big numbers. We take that total memory then and chop it up into what we call concurrency slots. So these are fixed sizes of memory that are allocated per distribution. There are 20 concurrency slots per DW500C on Gen2, and there's 4 concurrency slots per DW100 on the Gen1 platform. So we have concurrent queries, we have concurrency slots. Those come together here on this diagram where you can see the number of concurrency slots and the concurrency that fluctuates over the scaling up of DW100. So this is intermixed both Gen1, Gen2 service levels along the x-axis, and then the concurrency slots and concurrent queries on the orange line going up on the y-axis. So you can see here at DW100, we support, like I mentioned, 4 concurrency slots. So a query itself has to have, at minimum, 1 concurrency slot to run. All right, so that's how we can support 4 running concurrent queries at DW100 and 8 at 200, and so on and so on. Where you start to see differentiation between the blue bars, and the actual concurrency line, that's where we're starting to hold back some of the concurrency that is available to ensure stability of the system. So this gets into that same scenario around the 7,000 queries sort of issue that we have, and making sure that the system stays stable. So you may ask yourself, well, okay, if you've got more concurrency slots than you're allowing concurrent queries, what the heck do I do with that, right? Well, how's that any good if I've got concurrency slots on memory that's on the table, but I can't actually have additional concurrent queries to leverage it? So this is where the actual resource classes now start to come into play. So I can configure resource classes that actually consume more than 1 concurrency slot, and therefore then I can use all of the available concurrency slots that are on the service. So carrying this kind of concept forward, so the resource classes are basically how you're going to allocate memory per query. They're coupled with a login. So SPAD role member is how you move people in and out of the resource classes. There are 2 types of resource classes. We have both dynamic and static resource classes. And a couple things to note here on the bottom. Not all queries actually consume or require resource classes, things like metadata operations. If you create a table, if you're querying DMVs, those sorts of things. And then also, lastly, small resource class is the default resource class. So dynamic resource classes, kind of as the name states, dynamic resource classes are most beneficial if you have a fluctuating amount of data volume. You can assign a login to a resource class, scale up and not change any code, and actually have more memory allocated to the resource class. All right, so these are certainly ideal for scenarios where you may have a fluctuating amount of data volume coming in. You can scale up, run queries, and actually have more memory be allocated to the queries, scale back down, not really change any code, and then have that memory be right sized for the data volume that you're getting. The drawback with dynamic resource classes is they don't offer more concurrency as you're scaling up. So if you're scaling up to try to run more things in parallel, this is where static resources come into play. So static resource classes allocate a fixed amount of memory per query, regardless of which service level you're running at. So if I run at DW1000 with static RC10, I get 1 concurrency slot. If I run at DW3000C with static RC10, I still get 1 concurrency slot. So these are going to be essential when you want to scale up to actually be able to run more things in parallel. If you're able to size your ETL load that you could run with something like static 30 or static 40 resource class, and then you want to run more of those pipelines in parallel, you could scale up, keep the same static resource class, and now have memory grants be allocated to more things, more concurrent things in parallel. Okay? So let's kind of bring it all together here, back to this kind of graphic. So considering a scenario where I'm going to run DW6000C, I've got a certain amount of, fixed amount of concurrency slots, small RC in this case, per the definition for small RC on DW6000C. Small RC gives you 7 concurrency slots. If another query comes in at static RC10, that's going to consume 1 concurrency slot. Maybe some more queries come in, and then a static RC20 comes in. Static RC20 leverages 2 concurrency slots, and then you see as more things come in, the graphic fills up. So the key here, the key takeaway that I want you guys to have is you can run both dynamic and static resource classes together at the same time. They can coexist. They can operate together just fine. I can run my dynamic resource classes to do my data loads, understand how that's going to behave within the dynamic resource classes. Perhaps I have a fixed amount of dashboard queries, or I'm allowing my data scientists to come in and run queries that way. I can assign them to static resource classes and know that they'll have a level of concurrency and a fixed amount of memory that's being granted into their resource classes. Okay, so now that you're all ninjas in how resource classes work on SQL DW, let's see what we did here in Gen2 to make them better. So the first thing we did is we went after and changed the behavior of the small resource class. So on Gen1, we had this legacy behavior even since SQL DW was APS on-prem, where small resource class was a dynamic resource class, but it had a static behavior. And by static, it literally just only allocated one concurrency slot, regardless of the service level that you're on. Again, we're talking about Gen 1 here. And the reason we did this is we only had the dynamic resource classes at the time, and we wanted to provide a resource class that folks could use to get concurrency. So that's how small resource class, being in essence a static resource class, came to be. What ended up happening now in these POCs and pilots and things where folks would come on and provision a SQL DW instance and try it out, they would have these queries that are memory bound on DW1000, and they would scale up to DW6000 and not see any additional performance, right? Again, we've got a fixed memory grant. On DW1000 or DW6000, that query was still only getting 1 concurrency slot. So folks would have, in essence, a poor default experience as they scaled up. The majority of folks that come on and at least want to do an initial prototype on SQL DW are not coming out of the gate with just a high concurrency test. They're going to load up some data. We can see it in telemetry. Folks come in, load up some data, run at a few different scale levels, take some performance timings, and then see how things perform as they scale up. So this is where small resource class did not give a good default experience. The other challenge that we had with resource classes was there was an inconsistent amount of concurrency as you scaled up your DWUs. So you can see on this graph here, this is the medium resource class and what the concurrency looked like as you went from DW100 to DW6000. This one here will highlight specifically, so the DW1500 to DW2000, we actually go from a total concurrency or max concurrency of 7 to 5. So if you think of a scenario, and this certainly happened to a fair amount of customers, they've tuned their pipelines, they know they have a little bit more data coming in, they want to actually scale up their instance to make performance go a little bit faster. So I've got my ADF pipeline that's set up. I'm going to run 7 of these guys in parallel. Life's going to be great. Okay, let's scale up to 2,000. Things will run a little bit faster. All right, well, now we only support 5 concurrency with medium RC at 2,000. They go in and look at the DMVs, and they're like, oh, crap, 2 of these things are suspended. What's going on, right? So it was a poor experience, and it was just resource classes, concurrency slots, all this stuff is relatively complex to begin with. This was just kind of a rough edge that it was unnecessary and it didn't need to be there. And this whole thing kind of revolved around, kind of the punchline here with this is this orange table on the right-hand side. So we had a fixed amount of resource pools that we could use to determine the concurrency for a given service level. So if you're at DW 1000 on Gen 1, you've got 40 total available concurrency slots. If you divide that by 8, that gives you a max concurrency of 5 for DW 100. And these were, in essence, jagged edges. When you overlay them on the amount of concurrency slots that are available, you get this goofy-looking graph. What we did on Gen 2 now is we took away these fixed amount of resource pools and we went just with a straight percentage model. So now on Gen 2 with resource classes, for the dynamics, we follow this 3, 10, 22, and 70 model. And that just kind of rolls right off your tongue, 3, 10, 22, 70, right? So what that gives you now is, in essence, because it's percentage-wise, as you're going to scale up, you're going to see additional memory be added into your queries. Small resource class included is part of that 3% offering. So 100% divided by 3%, you get 32 concurrency with small RC. Same thing on down the line here. So 10, 4, and 1. So this is concurrency that stays constant regardless of what service level you're at. So I know this is a bit of an eye chart here. If we take a look, so this is an example here of medium RC with the Gen 2 service levels and the total amount of slots that are there, and what it would have looked like if we carried the Gen 1 model forward and what we ended up doing with the Gen 2 model. So you see here the number of concurrency slots that are allocated, DW 1000C to DW 1500C. Even though I've added 50% more resources, the concurrency slot stayed the same. So again, you're back to that scenario where you're scaling up to hopefully have something run faster. A memory-bound query is not getting any further memory allocated to it. It's going to, in essence, probably run the same amount of time. That's fixed over on the Gen 2 side with 4 to 6 now, so we've 50% increased the amount of concurrency slots, 50% more memory. It's going to run hopefully proportionally faster as you scale up. You may notice 8 on the Gen 1 side, 4 on the Gen 2 side, and say, hey, well, that doesn't make sense. These are concurrency slots, remember. And on Gen 1, these are 100 megabytes per concurrency slot per distribution. On Gen 2, we've done that 2.5 times larger. So they're 250 megabytes per distribution per concurrency slot. So you have a fatter chunk of your concurrency slot. You're actually getting more memory for that DW 1000 query here with just 4 concurrency slots. The other thing then is concurrency. As we saw in the previous chart, the concurrency was all over the place. Now with Gen 2, you have 10 concurrency that you can kind of set your watch to. Regardless of what service level you're at, you're going to have the same concurrency. Okay, so that's enough on resource classes. Let's take a look at Gen 2 performance with instant data movement. So before we get into the enhancements we made for distributed data movement on Gen 2, let's take a look at just kind of distributed data movement in general so we kind of get normed on terms here. So when we talk about distributed data movement, consider this scenario here where I have a table, product sales, and another table, sales account territory. So kind of your transactional data here in product sales, or your fact data, and then a dimension, something more domain type data and sales account territory on the right-hand side. So these tables, as you see with the DDL on the right-hand side, they're distributed, hash distributed. Product sales is distributed on account ID. Sales account territory is distributed on sales account territory ID. Now, when you turn this into more of like a physical perspective and how these distributions and how this data would be actually surfaced up to the physical compute nodes, you can see where things start to get into a little bit of trouble. So consider this query here where I'm doing kind of a standard top 25 sales by account territory name, all right? And I need to join the product sales table with the sales account territory table. Now, if I issue that query as is against these data sets as they're currently loaded, you'll see account 47 here on node 1 would be joined with account 37 on sales account territory. The table would literally return 0. This query would literally return 0 results, right? You'd have no matches from account ID across both tables. So what we do in this situation is we issue what we call a shuffle move command. So a shuffle move command builds a temporary object now that is redistributed to match the actual target table. We keep statistics on the control node so that we understand product sales is probably going to have billions of records. Sales account territory is going to have significantly smaller amount of records. It makes more sense to shuffle the smaller table and create this temporary object off of sales account territory. So that shuffle move operation then comes into place node-wise now, so I can join the tables together and return the result back to the user. So you're all now experts in how shuffle moves work inside of SQL Data Warehouse. So let's take a look here now at how this comes together from more of a data movement perspective. So that's from a query kind of semantics perspective that we saw before. But from a physical perspective, we have this separate service now called the Data Movement Service, or DMS. So the DMS is a separate standalone process that exists on every compute node and the control node. And what that does, that's basically the engine underneath the covers now that's doing all the data movement. It does our polybase loads, and it does anything that you just saw kind of in terms of shuffle moves or broadcast moves that are required for distribution incompatible query activity. So when that native shuffle, or that shuffle move operation kicks off, what ends up happening is data is pulled out of the distributed tables into the DMS service. So this is, again, a separate standalone process. Now it holds the data. From there, then it transfers data to the other partner DMS services that reside on the other compute nodes. They read the data in and then persist it into TempDB on that compute node. So the challenges with this, it's a standalone process. We have to reserve a fixed amount of memory for the DMS that we can't allocate, in essence, to engine running queries. It's a single-threaded bulk copy API, so it's not performant. As we're seeing advances in hardware, we still have a single-threaded activity. And the copy itself to move data between the DMS services is just not scalable. So we're getting additional bandwidth on our network. We're getting additional I/O bandwidth, and DMS is just not able to keep up. So what we did, we came forward with this improvement. We're calling it kind of instant data movement or non-DMS data movement. So in this situation, because we know how the tables are hash distributed, so we know the schema, we know the topology layout, we have all this metadata stored internally, we can pipe the results directly from the distribution databases into the target TempDBs in the appropriate hash distributed format that we need to resolve the query. All of this can happen in parallel across the different compute nodes. So what we get with this, data doesn't leave the engine format. We're in batch mode, so there's a minimal amount of overhead. And this sort of operation where we can push data directly into TempDB on the other compute nodes is very, very scalable. So we're able to leverage all the cores and the network capacity that we have. And by far, my most favorite part about this is the last one. This is a free improvement. So you don't have to put some sort of label in your query. You don't have to rewrite something some way. This just happens for you automatically, all right, on Gen2. All right, anytime there's a shuffle move operation, this particular sort of activity kicks in, and we're no longer using DMS. All right, so let's take a look at a query here on Gen1, Gen2. Okay, this is Gen1 here. So this is the TPCH schema. This is query 14 from the TPCH data set. It's running on DW1000 on Gen1. I have the same data set loaded over on Gen2. We'll run it here as well. So exact same query. I've got them labeled here on the bottom so I can query the DMVs. So this is two separate systems now, DW1000 Gen1 running side by side with DW1000C on Gen2. So if I take a look here at the DMV, this is just pulling the last time that that particular label ran and then taking a look at the steps that were there to run it. So we can see here, we've got our famous shuffle move operation that we saw. We see now that the location here is running on the compute nodes instead of DMS. So there, this particular step shuffled 204 million records in just over 13 seconds. Taking a look here then, we see those same 208 million or 204 million records to be shuffled on Gen1 took over 30 seconds. So 2 times the amount of speed there, and you can see this actual shuffle move operation took place on using the DMS. So again, this was the exact same query, ran side by side on both Gen1, Gen2. One's leveraging DMS, the other one is just using the native data querying that we have inside of SQL DW. Okay. So that's pretty much the content that I had for today. Just a couple slides to kind of wrap up here. So with Gen2 and adaptive caching, the advances we had on the hardware side, some of the changes that we made with things like the shuffle move operation, we've certainly gotten ourselves into a position with Azure SQL Data Warehouse where we're performing very well relative to our competition. This slide here, you guys that want to download the deck, it has kind of an aggregate of the Gen2 GA announcement, further details on the adaptive caching, some further kind of details around the instant data movement stuff. And then the last two here were a couple of benchmark reports that have been put out. So Gingham did a benchmarking report where they compared Azure SQL Data Warehouse to Redshift using the TPCH 30 terabyte results, and SQL Data Warehouse was better than Redshift on both a price performance perspective, so just performance also relative to cost, and then as well as just a straight line performance perspective. So regardless of cost, if you had a blank check and you wanted the fastest data warehouse that was out there, SQL DW would, for this benchmark, be number 1. Fivetran also just released a benchmark, their data warehouse benchmark. So for that they use TPCDS 1TB. Not sure why they chose that scale point, but they chose a 1 terabyte TPCDS benchmark. For that again, we finished number 1 on a straight line performance perspective, and that was compared to Redshift, Presto, and Snowflake. So from a straight line performance perspective, DW also won that one as well. Okay, And then we do have some further sessions here at Ignite. So Kevin's going to do a theater session tomorrow. Make sure you show up for that. Give him all sorts of questions for sure. He has another theater session later in the week as well, tips and tricks, and he'll cover some optimal loading stuff tomorrow. There's some customer stories as well, so certainly try to catch those sessions if you can. Okay, folks. So, Q&A. Folks have any questions? I do have socks to give folks. SQL Data Warehouse socks. It's almost winter. You can put 2 pairs on. Keep your feet warm. But please do step up to the mic if you have any questions. Thank you very much.